This is a controller for a very old disco lighting effect called Arcline. And the reason I've got this is because I'm creating a little unit that we can use this off the lighting desk via DMX. And the base unit, the unit is very retro. It's very much from the past of disco, but it's a very good effect, which is why we're going to be using it. The open terminal in the back is very common of that era. It's how disco lighting was hooked up. We've got two inputs. We've got an audio input, and we've got a disable input, which I'm going to be using to interface to the DMX. The unit itself has two knobs in the front, and it connects to sections of plastic tube with these xenon strobe tubes mounted roughly 500 meters apart inside. And typically, the usual tube has 4 of these units and some control circuitry, and then sort of what you might call slave strobes. And when you use this unit, if you turn it on to, say, for instance, repeat, and you set a speed and you set the repeat rate, then bright pulses of light, and I mean really daylight visible bright pulses of light, will rocket along those plastic tubes. This has been through the wars like most of these units. It's a very, very old unit. It goes back to 80s. So the options it's got, you've got the repeat, which will, if you turn it on, it will start firing those pulses. You've got single flash, which will just fire a single pulse. You've got run out. If run out's on, then when you fire a flash, it will run the full length of the run. But if you had run it out and you had it running and it was chasing the flashes and then you turned it off, they'd stop instantly. And you've got audio input, which enables the ability to receive an audio signal at the back, and it will pulse the lights. And this, you'll kind of get a beat effect where the beat will send pulses of light along the tube. The back of the unit has the connections, and it may look a bit dodgy that it's all exposed like this, but this is how disco lighting of that era was made. It was designed to be mounted into racks, not even 19-inch racks, although you could get adapters for it. But so exposed connectors in the back. We've got the mains in, we've got a fuse, we've got 2 jack plugs in. One is a stereo input for audio, and one is a enable input. They call it disable, but actually when you enable it with a voltage above about 6 volts. The circuitry inside is kind of the power supply for it. This transformer down here is the audio coupling transformer for the audio input. All the circuitry is effectively live at mains voltage. So the mains cable comes in, and the first thing it does is it goes through this fuse, and then it goes to a bridge rectifier. And then the circuitry takes a tap off that rectified mains voltage supply, and then it's put out to here. So you get very high voltage, it says here 350 volts peak DC going out along these connections. There are 4 connections. It only technically needs 3, but if you've got this unit mounted a long way from the strobe tubes themselves, then you have to run a 4-core cable, and effectively the negative and the sort of control negative and the power negative go separately until they get close. And the reason for that is if you ran a long cable to this just 3-core cable, there's a possibility that the voltage drop across the negative connection would actually cause so much interference that it could actually effectively cause false triggering. It would make it behave erratically. So that's why you need the 4-core if you're doing a long run. The circuitry inside is all CMOS based. It's CMOS logic chips with a lot of discrete circuitry here, and we'll take a look at the circuitry and how it works afterwards. But the gist is that you've got the 3 cores going out, and one of them, note the earth wire here, it's really not earth, and that's a bit of a problem. You've got the brown wire is actually the positive rail, the earth wire is the negative rail, and the blue wire is the data, the signal that actually controls the strobes. And unfortunately, as was so common of disco equipment of that era, they just use standard connectors, and that means, unfortunately, that Arcline has basically mains in the earth pin of this connector. So if you were to actually plug something like a metal appliance into this lead that comes out of this, it would be bad news. It's just round about that era, these connectors weren't heavily in use for things like this, so ultimately they used what connectors they could get, mains connectors, and this is so you have to be careful with the old disco equipment. Just remember that none of its connections are necessarily what you might call standard. So let's give this a test. Now I'm going to focus down onto the let's focus down onto the strobes. And I'm going to plug this in and everything will go horribly live because it is, yeah, it's all high voltage. So I'm going to keep this cable away from there. I'm going to position that. I've shortened this run. This was just a section I had for test purposes. And these are normally, the tubes are normally 1/2 meter apart, which is almost about 2 feet. There's also different capacitors. I replaced this capacitor because that one had oozed. The one there had oozed. So let's plug this in now and hope it doesn't go bang. Well, or hope it does go bang. And press repeat. And set the speed up high. Okay, and let's turn the speed down low and see, is it even going to catch that? You know, the flashes are so fast and intense that they're not necessarily even being caught in the camera because it is really high power. It's making the whole room flash here, but you're not necessarily seeing that because it is so fast that the camera shutter is effectively not catching it. But the tubes are flashing in sequence. If there were the full 4 in this set, they'd run along the 4, and if you connected loads of tubes together, it would just keep running the full length. So I'm going to unplug this now and then proceed very gingerly because these are now charged up to about 300 odd volts. So I'm just going to pause and take a look at the circuitry and then we can see how this actually works. So let's start off with the main control unit first. We've got the mains come in, goes through a fuse, goes through that big bridge rectifier, which actually feeds all the xenon strobes in the chain. There's a 100 nanofarad capacitor across that for, well, I suppose ultimately just removing electrical noise. There's a resistor and an LED. It doesn't light very brightly, it doesn't have to, so they've got a fairly high value resistor. They've got a fairly high power 20k resistor in the unit, and then they've got, hold on, these are Zeners, two 16 volt Zeners, and that creates 3 voltage levels. It has the 0 volts, 16 volts and 32 volts. Now, when I say 0 volts, I don't mean this as reference to ground in any way, effectively it's a negative rail, and compared to other voltages, it's a starting point. So I call that 0 volts, but it's not at 0 volt with respect to ground. The output of the power supply then goes to the logic circuitry. I'm not going to draw the control system's logic circuitry in too much detail. I'm just going to draw it as blocks because there's an awful lot of circuitry. It would take a very long time to reverse engineer it. It would be very complex. So we've got the block of logic that runs at 16 volts, and it's all CMOS, which it means that 16 volts is absolutely fine. We've got the audio input has 2 resistors, 2 10k resistors, I believe, 10k resistors, feeding an audio isolation transformer, which then gets filtered by an op-amp to create the pulses from the sort of beat. The disable input simply, or enable input really, has a 2.2k resistor and shares an LED of an opto-isolator. So that means that although all the circuitry is live at mains voltage, the audio and the remote inputs are all isolated. On the output, the control output has the ability to go between 2 voltages, well 3 voltages. It can be 0 volts, 16 volts or 32 volts. And the way they do that is the logic generates what I believe are the clock pulses via this diode so that it can control the output at 16 volts, 0 to 16 volts. But also I'm thinking it's the sync pulses that fire the pulse along the line. That's 32 volts, and to switch the 32 volts rail from the logic, it has to go via what's called a level shifter. So the 32 volt rail has this transistor which would normally switch up to that and via that diode to the output. But it's a PNP transistor and it's held off by the fact that it's pulled up to the rail by that resistor. When this transistor is turned on to the lower voltage rail, it pulls that rail down, the base of that transistor down, and turns it on. So it's just 2 transistors used to convert the voltage level. And that means the output, as I say, can be either 0 volts, 16 volts or 32 volts. So that covers that bit. Now, to give you an idea of how the tubes are being flashed, I'll show you the circuitry afterwards. The tubes use a standard strobe circuit, quite common in beacons, in, you know, for photographic studio type stuff. You've got the high DC voltage come in that runs along these wires here, and it goes through a diode, through this high power resistor, that's this resistor here, And then it charges this capacitor, which is, in this case, well, we've got two of them. It's this capacitor here. And it's notable that these resistors, the leads actually fold round, are bent back, and they've held them down and soldered them. And the reason for that is that if something goes wrong and those resistors start dissipating power all the time, they get very, very hot. They're only designed to be operated for a short period of time to charge these capacitors. So if something goes wrong, like the capacitor shorts out and these resistors just start dissipating power all the time, the solder will melt and these wires will just ping up, and that will effectively disconnect the circuit. It's just a little safety feature. It's very nice. So we've got the capacitor's charged up. There's a 2.2 megohm resistor across the capacitor to discharge it and sort of make it safe. I have checked, I've given it the finger test, and they are all fully discharged. And then the xenon tube is directly across that. So the voltage is effectively across this xenon tube all the time, but it can't strike because that's below the sort of striking voltage. It has a conductive layer. If you look at the inside of this, you'll see there's a sort of conductive paint on the inside of that, with a band here connecting to this little transformer. And that's a trigger transformer. It puts out something in the region of about 4,000 volts. And when it does, that pulse is capacitively coupled through the glass, and that's what strikes it. And once the gas has been ionized by that high voltage pulse, it dumps the capacitor. It actually dumps all the current out of the capacitor, creating that brilliant blue flash. And then when it reaches a sort of low voltage threshold, that cuts back off again. The trigger transformer, this is the trigger transformer here. It's got this sort of what you might call a low voltage winding and the high voltage winding. Great transformers, by the way. I ended up using these in my fairground strobes because Mode were really good at supplying components. If you needed any of the components from the Arcline, even if you said, I'm using it for a different application, they were saying, no problem, we get these, a lot of these, we can supply you them. And they didn't charge an awful lot for them. It was very good. Very good transformers. Those transformers have the primary, and it's charged via a diode, a high value resistor. It doesn't have to be low value because it's a very tiny amount of energy that's involved in these. It's almost like a static discharge. And that charges a 100 nanofarad capacitor that's in series with the primary winding of the transformer. So that charges up to the point that this zener kicks in and just caps a voltage. I think it's around about 100 volts it caps it at. And when it's ready to get triggered, there's a thyristor across that. And the thyristor is normally pulled to the negative rail by the 100 ohm resistor. But when the control circuitry gives a positive pulse, it's coupled through that capacitor, it fires the thyristor latches on, and effectively then it bridges this end of the capacitor and this end of the transformer and shunts them together, and the current flows very quickly. The capacitor discharges instantly through the thyristor, and it creates a very high current pulse in here, which is coupled across and creates the very high voltage spike across here. It's used to trigger it. So that's how the tube bits work. The tube itself has a master control circuit board at one end. Now, that's fairly visible, isn't it? It's a bit dark-ish. I shall bring the brightness up, but I'll probably have to take it down afterwards. So let's bring the brightness up like that. Is that going to be too bright? I think it's all right. It's got the circuitry at this end, and it effectively derives, just like the other one did, it derives a 1632 volt supply. And it takes the signals in and decodes them using voltage level detectors based on a little Zener diode in there at what's called a 4093, which is a quad NAND Schmidt trigger, which they've actually got them, they're just using it as 4 inverting buffers in this case. And then there's a 4017. The 4017 is a counter that sequentially counts along its outputs, and that's what's used to fire all the strobe tubes in sequence. So now I'm going to put that out the way. I'm going to bring the paper in. It's going to be really glary. I'm going to have to tame this down again because I have reverse engineered the circuitry completely. This is going to be so bright. That's better. So the signal comes in and it is either 0 volt, 16 volts, or 32 volts. If it's 16 volts, these chips operate at 16 volts, so it's via a resistor. If that was, say, a positive input, this is configured as an inverter, and it also has thresholds, so it actually sort of squares the wave off a bit. And then that gets inverted again. It's odd they've used them this way, but I think it just made sense because of part of the other circuitry. So that they've got these NAND gates that are just being basically used as inverters and squaring the waveform. And that just refreshes the signal. It doesn't, because it's two inverters after each other, it keeps the same polarity. And what you end up with is a nice solid clock for the 4017. That's the one that's going to make the lights run along the output. It also goes via this diode to the output again. So basically speaking, it's taken the data stream in and it's buffered it up and squared it off and cleaned it up, and it puts it right back out again. So with every section of this tube, all the signals actually get buffered up. For the 32 volt level, it's a bit more complicated. If it's 32 volts, this Zener diode conducts. This will still actually see the 32 volts in here. It won't harm the circuitry because there's a resistor limiting it. And it will just see it as a sort of clock pulse. The 32 volts goes through, will exceed the voltage of this Zener, a little bit of filtering, a resistor and capacitor, resistor to limit the current, and then it also gets buffered through two of these, but it's notable that it's coupled as a pulse. And that pulse through this capacitor, as soon as this goes positive, that will go negative, couple a negative pulse, but then that will go, drag that, it's normally pulled up to 60 volts, it will drag it down and the output will invert again, it'll go positive, and it has a feedback effect because when this goes positive, it conducts through this diode and it drives the input hard. So what you'll get is a really solid pulse. It basically creates a complete new timing pulse. Whatever size of pulse came in there, it will always put out a new pulse based on the value of this capacitor. And so that puts out a sharp pulse, which is coupled again through this capacitor, and it goes down to this sort of reset pin here. Now, the 4017 is a sequential counter. If you clock it and the reset is low and the clock inhibit is low, then it would just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would just count along the pins from 0 to 9. Continually, it would just loop round. However, in this case, they're only wanting it to count 1, 2, 3, 4 strobes, and then they want it to stop. So what they do here is they have the reset pin. Right, let's work out. It goes 1, 2, 3, 4, and then at 4 it stops. And what actually happens there is the 4 goes high, it inhibits the clock input, so it stops on 4. And it also, because that's now high, this diode is not active because it comes active later on. And that means it's waiting for the next reset pulse. When it gets the reset pulse, it goes back to 0, clocks along, and then stops again. But when it's actually been reset, this pin 4 goes low, and say the first pin's high. It gets a bit complex, sorry. What actually happens there is that because the clock inhibit is low, it actually pulls the reset down. It means that if this was just given a brief pulse for the reset, then it will then take over and it will hold that reset low to let the chip run through until it gets to 4 again. So it goes 1, 2, 3 strobes, 4, but it also then puts a signal out to the level shifter in the next bit of the circuitry. And what this basically means that this is providing the clock, and it doesn't matter that this is running all the time. This will only go 1, 2, 3, 4 when it receives this sort of trigger pulse. And it receives its trigger pulse by decoding it from the 32 volt level. That fires a pulse that resets this. It runs through and then puts the signal out to the next tube to tell it to actually pulse. So effectively, when it actually gets to 4 and puts that pulse out, it's actually firing the next tube in line via the cable that connects the two units. The other bit of circuitry here is the level shifter. I should bring the two of these in together. I'll maybe just zoom out just a tad so they can be seen. The output from the 4017 here to raise it up to 32 volts is coupled via this capacitor, so it's just a pulse. And it turns on this transistor, which again, this is a level shifter. And when this transistor turns on, it pulls the base of this transistor down, which is PNP, so it goes via that diode to the output. So that's regenerated the signal to actually pulse and trigger the next tube. The clock, which came through in this circuitry and was refreshed, it was squared up again, went through this diode, and that diode is actually this diode here, and it goes to the output. So again, you've got the 0 volt, 16 volt, 32 volt level combined. And the power supply in each of these little sections is just the same as the other one. It's got a diode, it's got the two, instead of one 20k resistor in the main unit, because it's got a lot more circuitry, it's got two 27k resistors, the two Zeners, and the two capacitors, and that's what creates the 0, 16 volt and 32 volt supply. So it maybe takes a bit to follow through what's happening here. But once you realise that how it works, it kind of makes sense that if this was permanently held high, this is permanently held low. Let me try and remember how this works. It's permanently held low. The positive pulse would actually reset that, and then when it's in action, because that's low, that stops any further pulses coming in until it releases it. So it's all very logical, and it's nice that it refreshes. That this circuit board takes a signal in and then completely reconstitutes and squares it up. It means that you can run a very long run of these without the data getting garbled or sort of interference causing rogue triggering of the tubes. And you know, that just leaves one thing. I want to actually see this waveform. I want to see what it looks like. So I'm thinking of connecting the main unit to an oscilloscope to check that out, but I'm going to have to work a way around the fact that that's mains voltage in that unit. I may have to power it some other way to connect it to the oscilloscope safely without damaging it. So I'll be back in a moment. I'm going to try and do that right now. So that's the oscilloscope hooked up now, and to do so safely, because this circuitry operates at mains voltage in normal use, I've had to run an external power supply from my bench supply set for about 35.75 volts. And there's a 220 ohm resistor to limit the current, and that's basically emulating the higher voltage power circuitry, which uses a much larger resistor. And by using the lower value resistor, I can use a lower voltage to get the same effect. So all I really needed was to exceed the 32 volts of the combined, the Zener power supply. So I've got the negative connection, the positive connection through the resistor, I've got the negative reference for the oscilloscope, and the probe is hooked onto the pulse output that sends the data along the line. So let's take a look now. I'm going to turn the light off so we can see the scope better, because it's very thin pulses. And you can see that it's roughly one every roughly about 24 clock pulses is one of the pulse initiation pulses. And the first thing that's surprising me, well, let's zoom up on this. Let's stop it. Let's just fill the frame first here. And then zoom in a bit. And the interesting thing is that I was expecting the base to be 0 volts with 16 volt pulses for the clock and 32 volt pulses for the pulse initiation along the arc line. But in reality, that tends to stay at roughly about 16 volts, and it goes a negative going pulse transition for the clock and a positive going pulse transition for the pulse initiation along the length of the arc line. So that's quite interesting. It's slightly different to what I was expecting, but it is showing that it's got the 0 volt, the 16 volt and the 32 volt threshold levels. So that solves the mystery of how Mode Arcline worked. So here's the interface box I've built so we can run the Arcline off DMX. And rather than go with just a one-off industrial enclosure with all the sort of DIN rail and the glands in it, I got one of these standard outdoor waterproof boxes that comes with the built-in 4-way shoe inside. And that means I can plug in 12 volt power supply for the DMX decoder. I've put in a bit of DIN rail, so we've got a relay for switching the power to the output, and again, the power just loops, it comes out a plug and goes straight. The live gets broken through the Omron relay. The choice of an Omron relay is because it's a proper industrial relay. I didn't want to trust one of these ones, and it means this whole board can be kept at 12 volts. I've got a DMX 5-pin plug-in socket mounted onto the case, so the cables can be accessed externally. And that comes up to the end, gets decoded. We can set the address in the switches here. And it means that one relay will bring on the Omron relay, which will then power up the system. The other relay sends a low voltage signal out from the 12 volt side to this with current limiting to make sure it doesn't get short circuited. And that will enable the Mode Arcline controller. And the way it works, it's actually working quite well. When you power it up, when you pulse the control signal, it will send a pulse immediately along the arc line at that point. And if you hold it on continually, it will then run at the speed that's set in the controller. So it's going to work out quite well, I think. And by using this universal box, it means that, you know, it's not just going to be used this year. If we have other applications in future years for an external box with mains feed in and various power supplies or controls locally to maybe a special effect, you just don't know what's going to happen in the future. But it means this box can be repurposed. It's not just a one-hit wonder and then it's, you know, gets binned after that. It's going to have other applications.